Proper, Arpita, we can start.
Okay. Ladies and gentlemen, a very good afternoon to all of you. As you may be aware, the IDP in climate, the Interdisciplinary Programme in Climate Studies at IIT Bombay has completed 10 years of its existence, and we began our decadal anniversary celebrations with a grand inaugural ceremony earlier this year in May. Understanding the Earth's climate system and the interactions between its components require an amalgamation of expertise across different domains. The initiative of improving diversity is not therefore a mere question of social justice, but is also necessary for the flourish of science. A small step is taken by the IDP in climate studies towards the global collective on improving equity, diversity, and inclusivity. And one of the highlights of our year-long celebrations is a series of distinguished lectures by women scientists working on climate science and policy, featuring global experts and thought leaders. This is the first lecture kicking off this series, and we are very, very pleased to have Rama Govindarajan, professor at the International Center for Theoretical Sciences, Tata Institute of Fundamental Research in Bangalore. Professor Govindarajan completed her BTech at IIT Delhi, PhD at IISc Bangalore, and postdoc at Caltech. And before TIFR, she worked at the National Aerospace Labs and the Jawaharlal Nehru Center for Advanced Scientific Research. Her research interests lie primarily on fluid mechanics, instabilities, vortex dynamics, particulate and drop flows. And in her own words, she was a nerdy kid who sat on the first bench, but was also very boisterous. And the one thing she says she implements in her home and her life is symmetry. Today, she will be talking to us on spatial patterns in the Indian monsoon, and we absolutely look forward to a lovely talk. Thank you, Dr. Govindarajan. You may begin your talk now.
Thank you, Arpita, for that very nice introduction and for the invitation. You can see my cursor. Hello?
Yes, we can.
Okay. Okay, so the work that I'm going to be talking about is a couple of years old by now, because it's come to a standstill just because there's no student working on it, but hopefully it will take off again. It was done with all of these collaborators. Amit is now in IISER Pune. Vishal and Shamriddhi are my colleagues in ICTS. Shrikar is in TIFR CAM. And the more important part of the work was done by these two people, Advai Mitra, who's now on the faculty in IIT Kharagpur, but was initially a postdoc with us, but he's continued to work with us on this problem. And Arjun Sharma, who was a one-year student, who is now in Cornell finishing up his PhD. Okay, so everybody here in this audience knows about the monsoon, but just to get into it, I thought I'll just talk for a minute or two on the salient features of the monsoon. We all know that in June, July, August, and September, this is called the Indian summer monsoon time, and almost all of India, except some part of Tamil Nadu and so on, get a lot of rain in this period. 70% of all the rain we get comes in this period. And it's called reliable typically because, like, on an average we get 85 centimeters of rain, with 10% less or more being considered normal. So, and the interesting thing about the monsoon is that if you line up all the onset days together, like Sulochana Gadgil has done in this figure, you get a very, very sharp change in the amount of rainfall. So you see that the monsoon is a dramatic event, and it's also dramatic in what it does to India. Like in a few weeks, it goes from this to this. So, and we know that it's not very well resolved in models, and so we need to study it. I've just put this photo of the Paris rainfall, like a typical European city's rainfall in comparison to the Indian monsoon. You see that this dramatic thing is very unusual. Okay, so then we said it's reliable and it's to within plus minus 10% on most years. And so, like, on very excess rainfall years, you get maybe 20% more, and on very deficient years, you get 20 to 30% less. So on the whole, it looks reliable. But daily rainfall is very difficult to predict, and each location is very different. In an excess monsoon year, some places may be facing drought-like situations, and the other way around. And even in the middle of reliability, like, I like to show this because this is Bangalore, where I live, and on the same latitude are Chennai and Bangalore, practically the same latitude. And like, it's a few hours drive from one place to the other, and you'll see the kind of difference in rainfall. Like, this thing gets so many millimeters of rainfall every year, like, and Bangalore gets 200 and Chennai 340. So, and you also see that the times of year in which the rainfall occurs is very different. So, like, this local behavior is very important, and that's one thing we're going to talk about. So there's two papers which are highly related to our work, but I mean, they're not like our work in many ways. So I won't be discussing them in great detail, but I just want to bring these to your attention. And in particular, people who are interested in this kind of work may want to, talk more about our method, and hopefully they will like some things about our method. So, since some of them are in the audience, I see Raghu in the audience and Subimal in the audience. So, like, the idea we said is to find spatial and temporal patterns in the monsoon rainfall. And how do we go about it? So, let's just see if there's any spatial pattern in the monsoon of 2008. So, we've used this 1 degree by 1 degree gridded data, which we're going to use a lot in the rest of this talk as well. And let's just watch a movie of daily rainfall. So you see that it's a horrible mess. Like, we can't really come up with any particular spatial patterns or things like that. So, like, if we look at a movie of the raw data, it doesn't tell us too much. That's the basic moral. But the point is that there's a lot of hidden stuff in this daily rainfall itself. Like, if you look at it in hindsight from our patterns, you'll recognize signatures of our pattern in this. And that's what we are going to discuss. So I won't show the whole of it. It goes on in a similar way. So we started on this work some 6 years ago, and we wanted to do something to understand the Indian monsoon. Of course, that's not an easy job. So, like, we started by learning something about the Indian monsoon. For example, by looking at Sulochana Gadgil's lectures, things like that. And we wanted to come up with an approach to bring about some different kind of spatial patterns. And in particular, we wanted to come up with daily patterns of the rainfall, daily spatial patterns, and also temporal patterns in locations. We will talk about that. So the basic idea in the back of our mind was that the monsoon is a dynamical system. Like, any non-linear complicated process is indeed a dynamical system, right? And then, like, it's got, like, other sources of noise which make it, even worse than a regular, large scale dynamical system. The noise actually makes small scale changes. For example, you could have a cloud band. You could be part of a very cloudy system, but locally it may not be raining in one place. So that could be because, local conditions for rainfall are not met due to some, reasons which are not very clear to us, and which may not even be included in a simple-minded dynamical system. So, like, it's a noisy dynamical system. This is what we're going to approach it as. And so there is an underlying dynamics which is more large scale and easier to understand. And the actual rainfall is a probabilistic manifestation of this underlying basic dynamics. So can we, like, look at this probabilistic haphazard manifestation and come up with some underlying features which can be describable by some underlying dynamics? That's the long-term aim, and let's see how far we could go in that. So we use this approach of Markov random fields. As we go on, it will become a little clearer to you, like, what exactly we did. Right now, it looks like a bunch of words. What a discrete probabilistic representation is, we will see. So I'll only be talking about these 3 papers we wrote. The first 2 was Advai Mitra in the lead, and the third one was Arjun Sharma in the lead. And so the first paper was about rainfall patterns. What patterns can we get? And the second was about the consequences of, getting these patterns. Can we say something about the monsoon from these patterns? And the third paper was about a joint distribution of clouds and rainfall. So that also reveals some interesting features, as we will see. Okay, so as I said, the aim is to find spatial and temporal patterns in the rainfall. Yeah, spatial and temporal patterns in the rainfall. So obviously, like, a lot of people have been doing this over a lot of years, and they've got quite a bit of success in understanding some spatial patterns. So let us just talk about, in particular, the 2 papers we talked about earlier. So let us talk in particular about what the basic idea is and how our basic idea differs from earlier basic ideas. So, like, one a standard way to deal with this is to find empirical orthogonal functions. So in other words, you just take out the most dominant, something like an eigenfunction, a generalized eigenfunction of this behavior, and then you find, lesser and lesser important eigenfunctions in that order, and these spatial functions can be lined up in order of importance. And then, like, every day's rainfall, so, like, I've written R of T. So a particular day's rainfall spatial pattern, so, like, can be written as a combination, linear combination of many of these. So, like, each F is a spatial pattern. It's an array with a spatial pattern embedded in it. And so, like, you can take each F and multiply it by a component, which is a function of time. Like, for every day, it will be different. So every day is perhaps, some lucky days you can describe by a few modes, but there are other days which you'll have to describe by a very large number of modes. So it's not very instructive on what one day's pattern is like. So since we want to look at every day's pattern, the EOF is not a good approach for us. We could look at every day's pattern by doing k-means. That's a kind of clustering where you decide that you want every day. So suppose you have 122 monsoon days in a year. So let's take 1 year, and I want to say that these 122 days can be put into 10 clubs. 10 clubs, so like 10 clusters. So in these, each cluster, like, all similar days will be clubbed. So I say there are n clusters, and each consists of rainfall patterns which look similar to the other days in that club. So I'm just making them into clubs by just looking at who is close to what. So that could be one nice approach. We'll talk more about it later on. In the Markov random field approach, we do something entirely else. We say we want a small number of patterns, and many of the days should be the patterns on many of these days should be similar or describable by one of these patterns. So again, we're talking about clubs or clusters, just like the k-means, but we say that we'll not tell how many the n should be, but n should not be too large. Hopefully it will not be too large. And also, every day need not be a member of one of these clubs. If there are some outlier days, we can reject them. We can do a bunch of other things, like make the patterns more coherent in space. We can do a lot of other things. There's a lot of flexibility in this method. So the RT is not some linear combination of something. It's just one among a bunch of spatial patterns. So there are these theta I, where I goes from 1 to n. There are n spatial patterns. Each theta I is an array of dimension s. So if there are n spatial locations, then the rainfall at spatial location 1, spatial location 2, you line them up in a long array. So all the spatial locations have a representation. So I have the rainfall in all the days arranged in one long array, and I look at the rainfall of a given day. The R consists of, all the R1s, R2s. And that rainfall of a given day will match one of the I's. It will match or be close to one of the clubs. So we are making n clubs which look like this. So each theta I, as I said, is an S dimensional array. If there are S spatial locations, you have S being the length of that array. We could do something similar to time also, which I won't talk about. The important thing here is that instead of looking at this real number array, we are going to look at a discrete array made up only of zeros and ones. And this is going to help us in many ways. Like this is going to be, I mean, if you could actually take up this thing and do even k-means on it, you're likely to do a lot better or get more coherent and simpler patterns. But yeah, so we're going to divide it into zeros and ones. So what we do is the following. We look at every location's rainfall, for example. So first we start by, because every location is different, we want to say Z equal to 0 means dry and Z equal to 1 means wet. This is what we're going to say all through. Like we're going to just divide each day into dry and wet. And so like if we do that, and we want to convert our rainfall data into just a bunch of zeros and ones, how do we do that? First, we have to look at each location. For example, a place in the Thar desert may not be comparable to a place in Rajasthan. Like we should not define dry and wet for them in the same way. So like we make some initial guesses of these Zs, and later on things improve by the Arpita, I'm getting some notification from you.
Yeah, actually, we in the campus, we are having some kind of a internet outage, I think. Sorry about that. Please continue.
Okay, so like I press approve on what you've sent.
No. Just ignore that.
Decline?
Sorry. Yes.
To decline. Okay,
Yeah,
okay.
please continue.
Okay. Okay. So like we look at the probability density function of rainfall. So like each day's rainfall, each location's rainfall, if we look at it, so suppose I take just one location in the middle of Madhya Pradesh, and I'm looking at, there'll be many days which are dry even in the monsoon season. So the probability of zero rain is quite high. And then there's like some typical rainfall like this. So like each day's rainfall, each location's rainfall averaged over many years, or the probability density made over many years, looks something like this. And so like we said, of course they're very different in detail, but each of them we treat them as two two gamma distributions. So we treat them as a sum or a linear combination of two gamma distributions. So we model them in this way, and then according to where you are in the distribution, we decide whether it's 0 or 1. This is only an initial guess, as I told you. This is one of the initial guesses. In fact, like when we do our Markov random field iterations, you will see that I can start with the most foolish initial guess, and still we will come to some good patterns in the end. So instead of those arrays of theta I, we now have discrete arrays of theta I, which contain zeros and ones. So so I've written location-wise array in pattern cluster I. So there is a group of days who join together as a club. And in that group of days, this is a characteristic way in which like they have in each location, there's wet, dry, wet, dry, wet, dry, or whatever. So it's arranged in this way. So that is a characteristic pattern of a given bunch of days, a given club of days. Now, how do we find these clubs of days? How do we go about it? So first we decide who is related to who. And this is where the Markov part of the Markov random field comes. We say that each location is somehow related to its immediate neighbors, north, south, east, west, and it's related to the immediate times, yesterday and tomorrow, because we're talking daily. We have yesterday and tomorrow. So like these are the time things, the time connections, and these are the spatial connections. So like and all the times are lined up here, all the space locations are lined up here. So like there are edge potentials which are connecting these locations, and there are also edge potentials which connect the entire pattern to a given club theta I. So like whatever given club it's been assigned at that iteration. So like I have all these Z patterns. So remember that these are a large number of temporal locations a large number of spatial locations, and for each day and each location we have a Z, which is just a 0 or a 1. So like our whole game is to decide whether a given Z is a 0 or a 1. That's our whole game. And in order to decide whether it's 0 or a 1, that thing, whether it's a 0 or a 1, is going to depend on a whole bunch of things. So it's going to probabilistically depend on a whole bunch of things. It's going to depend on its neighbors in space and time. It's going to depend on, you know, the clubs that are existing at this time, and it's going to depend on whether it resembles one of the clubs or not. So it's going to tie up with that. It's also going to depend on the total rainfall. The Y's are the total rainfall here. So it's going to depend on the total rainfall on that day, and also like we can add edges on total rainfall of that location or things like that. So it's going to depend on the temporal clubs and the spatial clubs, or in other words, the spatial clubs and temporal clubs are going to be organized in such a way such that they represent many of these days. So this is the game, and you can see edge potentials between the actual rain and the Z. Obviously, like if it's a very wet day, I have to give, by high probability, I have to give a 1 to that Z. So that's how it's got edges which strongly connected to the actual rainfall as well. So like, so it depends on the actual rainfall. And one thing we can say is, suppose the actual rainfall in a given location is low, but all its neighbors have extremely high rainfall, then like the edge potentials can win over the actual rainfall and make this a 1. So like, because everybody nearby is a 1 by a huge margin, I'll call me also a 1, because I'll assume I'm part of a weather system. So our choice of Z depends on all of these things. Okay, and then I'd like to say that simultaneously, as we decide these zeros and ones, we also have to decide what are these canonical spatial patterns, the few spatial patterns who describe most of the days. So for this, we use what's called a modified Chinese restaurant process. Now, a Chinese restaurant process is a very standard algorithm, which is a rich get richer algorithm. In other words, like if you're already rich, you have a bigger probability of becoming richer. If you're already poor, you have a bigger probability of staying poor. So the rich get richer algorithm. So the way it works is that a human walks into a Chinese restaurant, and he or she sees these tables, some of which are occupied. I didn't draw the people on it, but imagine that some of these tables are occupied. Except that in our case, each table is a pattern club, and each human walking in is a day with its own pattern. So this, if a human walks into a Chinese restaurant, the human is more likely to join a table with many people already in it. And the human is very, very less likely to start a table of his or her own. The human is very likely to sit, unlikely to sit at an empty table. So with great probability, the human will sit with in a table occupied by many people, and with lower probability few people, and with very low probability start a table. We're going to do the exact same thing with these daily patterns. But why do I call it a modified Chinese restaurant process? Because a human doesn't care like whether the other people look like them or not. They sit in a table with more people. Whereas here, there's going to be a big edge potential connecting my day's pattern to some canonical pattern. And so like I'm going to look not just at whether there's many days already in that pattern, but also whether that pattern is suitable for me, whether that pattern looks like me. So then like if I am a day, I'll join a given table based on this. So that's going to happen at every iteration as we proceed. Okay, so now we're going to work with the Zs alone. We're going to give up everything about the daily rainfall, like the rainfall at every location. Of course, we'll remember the total rainfall of that day and the average rainfall for that location. But now that we've determined the Zs, we're going to work with the Zs alone. And we're going to create these edge potentials that I talked about. So like so I'm only talking about my immediate neighbors, like the ZT and T plus 1. And then with some probability, I'll try to align with my neighbor there. So that F is a user-defined number. But luckily, like we could choose a bunch of Fs and we get very similar patterns. So like we have a bunch of user-defined numbers here which change some things but don't change the overall picture. They change the details every time. And for spatial correlations, we don't always give the same number because, like, you know, this side of the Western Ghats is very different from the other side of the Western Ghats. So just because it's raining on that side, I shouldn't make it rain on this side. So we can't have, like, you know, the same strength edge potentials everywhere. So based on their overall correlations in time, over all the time, using the Rajivan data or some other data, we fix these edge potentials. So once the edge potential is flipped with some probability, fixed with some probability, the Z can flip its sign based on the edge potentials. Similarly, like these are the canonical patterns U and V, the spatial patterns and the temporal patterns, and there's a strong edge potential connecting a Z to its canonical pattern or its club. You know, the table where it sits, that table has its canonical pattern, which is made up of the mode of all the patterns who are sitting there. So this is also something which keeps changing in time as the members change. So like each canonical pattern is described by the mode of all its members. And so that's what we do. There's a strong edge potential connecting the daily pattern to the actual rainfall. So these are the things we do. And so like different days, different times can join a particular pattern, 1 or 2, based on this. So this is what we do. And we've used this data of Rajivan et al. As I told you. It has 357 spatial locations gridded data, and we use the thing in 8 monsoon seasons. And what we do is we do some iterations using this process called Gibbs sampling. So start with a guess distribution. It can be a good or bad one. We perform one iteration by choosing, so like already all the locations and all the times have a 0 or 1 attached to them. So now what we'll do is for each location, so if I go to a particular location in a particular day, I will use the conditional probability. I'll fix everything else. I'll not change anything else out of the canonical patterns, the daily rainfall, the neighbors, nothing. And I will, based on these edge potentials, choose a 0 or 1 by random method, but the most probable one. So like I sometimes will be flipping the guess value I started with. You can imagine that. And do this for every location and every time, at every time freezing everything else and taking the conditional probability of a 0 or 1. And then check how many flips you made. If you started with a terrible guess distribution, you'd have made a lot of flips. But after some time, what happens is the number of flips reduces. We never reach 0 flips, but we reach a kind of steady state in the number of flips we do between iterations. And after this, sorry, like I've written 100, we actually performed 500 iterations, and we got the mode of these distributions to get our canonical patterns. So I'll be going to results from now on. So like if anybody has questions on this part, it'll be nice if you ask them so that it becomes, I mean, our results become more convincing if possible. Questions from anybody?
We do have a question on one of your, but you know, unfortunately, I had to reconnect, so I've lost it. Shiba, do you have the question that was asked on the Z of array?
Yeah. You mean
Can you read it out? Can you read
Kashif
it out, please?
Akram? Yeah. So Kashif Akram is asking, why do you need arrays? It's not clear. If you already can decompose R of t in terms of Fj modes and A j of t coefficients.
Okay. Yeah, you can already decompose this. So like here you have an array of F. Do you agree with that? So F is an array which is a number at every location. It's a rainfall number at every location. I multiply that by some coefficient. Then I take the next F, which is also an array. I multiply that by another coefficient. I do all of this to like many modes in order to get the correct rainfall of a given day. in our method, it's not like that. We again use arrays, like everybody has to use an array for a space to represent space. So each spatial location has to be one element in that array. So we need an array to represent space. The only thing is that we want only one pattern to describe a day. We don't want a linear combination of many patterns. We want just one pattern to describe a day, and we want a few patterns which are going to describe all the days. So like every day is, joining one of these patterns, which is like 10 in number. In our case, 9 or 10 in number. Is this the question you asked, and is the answer clear? Okay. Any other questions?
Shiba, do we have any other questions
No,
typed
not
in?
yet. No,
Okay.
not yet.
Hi.
Hi.
Just this Raghu. Yeah.
Hi, Raghu.
Yeah. Hi. Was there any a priori physical motivation for this, or it's just an application of a technique?
No, it's not an application of a technique, because we've kind of invented this technique as we went along. So the idea was like, we saw this rainfall and we said, is it possible to describe it? So the basic idea was, can we come up with the simplest way to describe this rainfall pattern, simplest statistical way? And so like we tried a whole bunch of things, including k-means. So it wasn't that we had this technique beforehand which we could use on it, but we had to keep inventing, aspects of this technique as we went along. So like the first thing we thought is, let's make our life easy by making it a bunch of zeros and ones, not all the real numbers, because if we think of it as wet or dry, then we can very easily come up with patterns. The next thought we had is that, there's probably coherent patterns in space, but it looks very spotty in the rainfall. Maybe the clouds or the pattern, something else like winds or temperature. There's like large scale things in other variables which are manifesting as this spotty thing in the rain. So like, let's bias towards coherence. So like we made a method which would deliberately bias it towards coherence, like make it flip from wet to dry if everything in the neighborhood is dry, and if the previous day and the next day are dry, things like that, which enforce a higher degree of coherence than is inherent in the data. So this was the second idea, and the rest was like, just try to be fair to this, true to this, and invent a statistical method which will do this in a proper way. Is that a satisfactory answer, Raghu?
Yeah. So maybe when we look at the results, it will make more sense. Thanks.
Okay.
Can I ask a question? Am I audible?
Yeah, please.
Okay, I'm Aditi from Savitribai Phule Pune University. My question is a little confusion in my head about how you distinguish between these wet days and dry days. It's like a very binary, grouping. So I'm wondering, how is it that you also sort of represent the difference in the intensities? Because, when we are making groups of rainfall patterns, how much it rains in certain areas versus how little or more it rains in others will also contribute to these patterns. So if you just make a distinction, so how have you tried to address that part, if you have at all? Thank you.
In fact, like that is seen in this one. So the thing is that, let's look at this one first. So like these are all the Zs, and these Zs are 0 for wet and 0 for dry and 1 for wet at each location and each time. Is that okay so far?
Yeah, that makes
Now, do
sense.
I call it a 0 or a 1? That's your basic question. How do I know when to call it a 0 or a 1?
No, I'm asking is, so the three stations that you showed at the same latitude, right? One, the Bangalore, Mangalore, and Chennai. Each of them have different amount of rainfall. So,
Exactly.
but all three of them are wet, because say suppose on the same day it rains in all three stations, but different amount. So are they grouped under the same same group or same cluster, because they are wet?
So,
or do they get distinguished owing to the amount of rainfall that occurs?
Okay. So like we'll see how it works in the results. You'll get a little more, you'll be a little more convinced of this. Like right now, it seems like it doesn't seem too convincing, I agree. But what we have is an edge potential which is connecting every Z to its actual rainfall. Now this X is a real number and Z is a 0 or a 1. This real number will be called a wet or a dry depending on that place. So like, depending on its mean. So like if, Mangalore has a very, very high mean. So like, the same amount of rainfall in Mangalore will be called a 0, and that could be called a 1 in Chennai because in Chennai it never rains in this time. So like, yeah, like if I have some 2 millimeters of rain or something, it might be a 1 in some place and a 0 in another place. So it depends on, where you are on that distribution of X. So that has a edge attached to it. And also like these flippings, like flipping based on the neighbors looks a bit arbitrary now, but it'll hopefully become convincing as we go along. So did this answer your question, Aditi?
Yeah, it's a little more clear to me. Thank you.
Okay. And yeah, so like what we first did is we drew we first drew the distribution of rainfall in each location. And in each location, we decided what is dry for that location and what is wet for that location. So like that was the initial guess we started with. But yeah, so this already biases you towards like, that edge which connects you to your everyday's rainfall. So yes, like if like it's raining in Chennai by let's say 5 or 10 millimeters on a given day in the monsoon, then it will surely join the wet patch which connects it and Mangalore. That never happens in Chennai, but I'm just saying that it would be the same grouping. Shall I continue with the results?
Yes,
Okay.
I think so.
Okay, so like we thought that first we want to make these Z patterns of zeros and ones, and let's be kind to ourselves. Like if we look at the rainfall pattern, it's too spotty and messy, so we won't know whether we're doing it right. So first let's do it with cloud patterns, and the outgoing long wave radiation, as you all know, is a proxy for clouds, and where OLR is high, clouds are less, and the other way around. So like this is the raw data we just plotted, and you see like there is this cloud band. There is a clear cloud band, and we did our Zs on it, and this is the thing that we got. So these are the places where Z is 1, and these are the places where Z is 0. So it's kind of getting that pattern, although like here it's missing some light clouds, and on the edge, on the boundaries, it's going to always be bad. It's going to miss things because it's going to tie to its neighbors, which are now non-existent, and so on. But broadly, it seems to be getting like, we're sitting in this cloud band, or the cloud band looks like this. It seems to have got that broad thing correctly. So this is our MRF description, which we just got by flipping zeros and ones repeatedly and, starting with some arbitrary guess. And we're not doing too badly. So that's the thing which gave us some confidence that we should go ahead with this method. Now, we repeated that for rainfall, that whole procedure that I told you, and we get 10 patterns of rainfall. So we get something like 100 patterns, but 90 of those patterns are got just one member. In this Chinese restaurant process, among so many days, like 122 days, 8 years, and 357 locations. So like in the 122 days and 8 years, multiplied by 8 years, in those 900 something days, if only one day looks like a pattern, like it's sitting in a table by itself in the Chinese restaurant, we throw it away. So we ask like how many of these tables have a reasonable number of members, and how many of these tables have members across the years. So it's not interesting if like there is a pattern which occurs only on 1 year. So such patterns we don't want to consider. So we call them prominent patterns if they occur repeatedly in all the years and they occur in many times in a given year. So we get only 10 such patterns. And the beauty is that we ask how many days are members of these clubs, these 10 clubs. We find that 95% of all days are members of these clubs. And only 5% of the days are outliers. So we have a nice method which threw away the outliers and it brought in days which are kind of similar to each other. So this is like the main result which we were going with. And you see, and this is just in terms of the Z, the zeros and ones. I'll show you the real rainfall in the future slides. You see that this pattern is dry everywhere. Like here, it's not raining anywhere on the Indian landmass. Here also, except for, the Western Ghats, it's not raining. And here, like, except for something in the Northeast and bit in the Western Ghats, it's not raining. So these three look like relatively dry patterns. In fact, 1 and 3 look like rather dry patterns. And then we have this pattern 9, 7, and 5, which look like each other actually. Why they are different patterns is because their total rainfall is different. And this will come back to the question that you were asking, Aditi. So like these three look like very similar spatial patterns. So why are they different clubs? It's because they've got edge potentials to the total rainfall. So they are actually very different in their total rainfall, but in their physical appearance, like it's basically this central India patch and the Western Ghats. So these three are very similar in that way, central India and Western Ghats. So there's like relatively dry with maybe only Western Ghats. There's central India and Western Ghats. And some of these are northeast and Western Ghats. It's never not raining in the Western Ghats. So you have some typical patterns which look like northeast and Western Ghats. So we divided these things into 3 families, like raining nowhere, raining northeast and Western Ghats, and raining central India and Western Ghats. These can be divided into 3 families, and we'll come to that. So now I'm showing not the Z values of 0 and 1, but the actual mean rainfalls of all the members of that club, all the days which were in each of these patterns. And the beauty is that we determined this over 8 years, where all 95% of all days were close to one pattern or another. We repeated this for 111 years. We used the data from 1901 to 2010, something like that. And then we saw that all those days are also joining our canonical patterns, which are now predefined. So like 95% of days on all those years were also joining these patterns. So like over the 100 years, you can say there are some very typical patterns. And here, we discussed this 5, 7, and 9 specifically, the central India and Western Ghat rainfall. And you see that they're actually very different in their total rainfall, though physically they seem to be occupying similar areas, similar neighborhoods where it's raining. So these are the canonical patterns. And so like these can be divided into 10 families. The pattern 10 doesn't have too many members. It's like excess rainfall in the Northeast. It doesn't have too many members. It might be clubbed in with the family, which is like 4 or something like that. 4 or even 6. They're all kind of similar with Northeast and Western Ghats rainfall. So then, like, we're talking about what we've achieved so far. We've come up with a few patterns which are coherent in space. There are patches which are raining. So we've got that. We've seen that discrete has advantages over continuous, because if I did k-means with the continuous data, like instead of z equal to 0 and 1, if I use the x values, then like it will give me some strange patterns, because places with excess rainfall, days with excess rainfall in certain places will tend to be clustered together. So k-means won't get the real picture of what's happening. It will give me 10 clusters if I tell it to give me 10 clusters. And these are the kind of averages we get, which are not really representative of what is seen. So now if you go back to the monsoon of 2008, you'll start seeing days which are actually like one of these patterns. So this is just the same thing I showed you in the previous graph, but the color scale is not so brilliant, so you don't see it that good, but you can still see coherent patches here of Northeast and other things, and not spotty little places where it's raining a lot and biasing. Now, like somebody in the beginning had a question about the EOF modes. Like he seemed to ask, like when you have the EOF modes, why do you need to do all of this? So these are the first 10 prominent EOF modes. And you can see that not a single day can be described by these. Like we'll have to take linear combinations of all of these. We can't describe any day by these. So for our purposes, EOF is not a great way to go. And to our surprise, our results were insensitive to the initial guesses. And in many parameters which we compared, which is there in our paper, it's doing better than k-means and better than spectral clustering. It's doing just better than these things. So you can read the paper. I won't go into each of those comparisons because I'm nearing the end of my time. And it is more, so like this one we already talked. And we also said that if there are strange days like k-means and other things, won't know what to do with it, but this one will put them on a separate table. So that way we'll get only the canonical days. So then like these, as I told you, can be, put into 3 families. There's a dry family and there are 2 wet families, which are like Central India and this. And we can see the persistence time, like how many days does a pattern, like a daily pattern live inside the wet family? When does it leave this family? What happens to it? All those things can be got, like we can get these transition matrix. So here we've arranged the things according to families and you see these block diagonals. So if today's pattern is this, tomorrow's pattern is likely to be inside the block diagonal. So with high probability, it will be persistent for a few days. So this kind of persistence things we can study. That was just an example of that. We can see how often does each pattern occur. So in June, July, August, like are these patterns like equally probable? No is the answer. We can look at which pattern occurs when. So like we can see that pattern 1, 2, and 3, which were the drier patterns, occur quite a lot in June and September. Whereas they don't occur so much in June and July. They do occur, but not so much. And these wet patterns are very frequent in June and July and less so in July and August, sorry, and less so in June and September. So we can understand, like, what are the canonical patterns and how do these occur? Like, what are the different days which happen in July, August? What is typical for July? What is typical for June? All of this we can study. And now the interesting thing we see is that we divided things into all years, excess years, and deficient years. And we find that a similar number of days is occupied by a given family. So like, this dry family is the most common. Like 60 days of every monsoon season is occupied by the dry family, whether it's an excess year or a deficient year. But these 2 families are also occupied by similar number of days, which is interesting. Of course, in a deficient year, it will choose that member of the family which is deficient in rainfall. There'll be more drier patterns inside the Central India in the deficient year and more of the other in the excess year. But typically, these families are quite representative across all these years. And we can see the active and break days. So like there was this, Rajivan et al. Had given like classified various days into active and break. And we went by their definition, which we showed in the blue pokey things on given days. And by our definition, we chose like active patterns and break patterns. So we said, if today's pattern is among the excess rain days, among, those 3 patterns, 8, 9, and 10, we call it active. If it's among 1, 2, and 3, we call it inactive. And we see that there's a huge correlation, like wherever our reds appear, their blues also appear. So like this one, I'll skip in the interest of time. We did this joint thing with cloud and rainfall now. And this time we use different data, like trim data from 2004 to 2010, different years. So we wanted to see if that data, which is much more, many more data points, like half a degree as opposed to 1 degree, and it's different in many ways. So we got out of this 8 canonical patterns, not 10. And these canonical patterns showed like similar that family behavior, Central India and this northeast, some dry, except for this pattern, which we didn't get before. Most of them looked like what we have before visually. So we see this in this thing, we repeated this. Now we also showed that what you've got over land, we did this Zs and zeros and ones only on the land. But then on the days which belong to the club, we know the rainfall on the oceans. So we can see this consistent pattern over the ocean as well. So these are just those 8 patterns with the ocean thing also added and real data instead of the Zs. And what happens to clouds? Like there are 8 patterns in clouds as well. So we see that there is again a Central India covering cloud patch, and there is that one, then the Northeast covering cloud patch, and so on. And this is an interesting slide. which I want to spend a minute on. Now, we look for joint patterns of cloud and rain. So what we do is, instead of Z being 0, 1, Z is now a 2D array with two element array with 0 and 0. 1, 0, 1 for cloud and 1, 0, 1 for rain. So these Zs we now constructed, and now the Zs can be divided into 0, 1, 1, 0, etc. Namely, like cloudy plus rainy can be one pattern, cloudy plus dry, sunny plus dry, sunny plus rainy. So these are the four kind of behaviors. Fortunately, like when it's sunny, it's never raining. So it has to be cloudy to rain, which is a necessary condition. So there's very little yellow in these. Actually, it's hard to find any yellows. So luckily, like, it's consistent. Now, you can have sunny and dry, and those are these, most of the break days come under this sunny and dry kind of behavior. Whereas you can have cloudy and dry or cloudy and rainy. So cloudy and dry, you see, are these light blues. So you see that a lot of Rajasthan, this area, Gujarat, and Tamil Nadu, of course, is actually cloudy in many of the days, not on these break days, but on the active days, like this region is actually cloudy, but it's not raining. So these kind of insights we can get from these patterns. And again, you see the families even in the joint patterns. Okay, so this one also I'll skip in the interest of time, and this one also I'll skip. It was just like, because everybody does anomalies, we also did one-day anomalies. We did various anomalies, and we found our answers are insensitive to all that. So here we were asking about the anomaly, one-day anomaly, like yesterday minus today, or today minus yesterday, or tomorrow minus today. And we saw how cloud patterns go from one to the other, like through which anomaly pattern does it transition, things like that we studied. So since I'm running out of time, I'll just stop here and I'll give this summary. Like the MRF, we've just started and done some work. It seems like a promising approach. I hope I've convinced you on this. And we've shown that a few coherent patterns capture a lot of the story, like what happens in June, what happens in September, how can active days be defined? Are all active days similar? A lot of the story of this active break and these things are captured in this few patterns. And we get, like, some insights into the transition, like how persistent is going to be a wet pattern, how persistent is going to be central India rainfall, when is it going to transition, what is it likely to transition into, things like that. So, and these joint patterns are like interesting on as a first study, but we would like to try this with SSTE and a bunch of other things. And we would really love it if people in this audience were interested in, asking some of these questions with us. And we could ask, like, what happens with climate change? So, like, knowing we can ask, like, are these patterns still persistent in future years? We've stopped this analysis at 2010. There's already 10 more years of data. So do these patterns, are the frequency of some of these wet patterns changing, or what is happening with climate change? So thank you for your attention, and I'm happy to take questions.
Thank you very much. Yes,
thank you.
Yeah, so we do have a few questions in the Google Sheet that we have shared in the chat box.
Okay.
I'll read them out. Meanwhile, I request the participants to write in their questions in the Google Sheet or in the chat box. It's okay. I'll read it out from any of those two. So, Dr. Rama, the first question.
May I suggest, Shiba, if the listener is still tuned in, if he or she would like to unmute himself or herself and ask the question, that way we can have a
Yeah, that would be better, right? Yeah. So Poonam from IIT Gandhinagar, if you're there online, you can switch on your video and ask your question. Poonam from IIT Gandhinagar. Okay, I'll read out her question meanwhile. So Dr. Rama, her question is, since the same 10 patterns could fit rainfall in last 100 years, how does climate change impact to rainfall be observed or accounted for? Did the number of strange days increase over the years?
That's a very, very good question, Poonam, and I don't know the answer. And that's why it would be interesting to study it. Like in particular, we can see if these strange days or like excess, and in particular, most of the strange days were excess rainfall days. We noticed that most of the days which didn't fit into any pattern were these, torrential rainfall days. So like maybe, with extreme events increasing, it's what you're saying can be happening. We haven't actually checked that, but that would be an important thing to check. So like, and also like what the frequency of each of these patterns, how it's changing. I hope that answers your question, Poonam. Okay, we'll go on to the next.
So the next question in the sheet is from Srinivasa Polisheti. His question is the climate change are the climate change and recent extreme events sticking to patterns and groups?
So,
Dr. Ramakrishna, is that question from you?
Yeah, it's from me.
Okay,
Yeah.
you please go ahead. Hi, nice to see you again.
Yeah, thank you.
So your question is that with climate change, is this active and things happen? I mean, looking the same?
Yeah, actually in 2005, July 26, we had 944 mm in Mumbai.
Right.
So incidents like that, even cloud bursts in some places. In
Yeah.
Himalayas.
So I mean, most of those outlier days we noticed, which weren't fitting into the 10 patterns, were indeed days like that. But we didn't do a study of like how is the frequency of this different patterns changing over the years. So that would be needed to do to answer your question. And in particular, we haven't done the last 12 years, where a lot might be changing.
And as the climate change is unfolding, I think these things will be more extreme.
Yes.
Yeah,
Yes.
and will your model continue to evolve?
Our model will continue to evolve, and our model might throw up extra outliers. So it can actually tell us like how the extreme events are increasing or changing. So our model could do that. Like it could say that, fewer days are now following the canonical pattern. And also it could be that the canonical patterns themselves are being redefined with the years. So all of this may be happening.
Thank you, Dr. Rama.
Thank you.
So is there any other question you are going to read out, Shiba?
Hi, Professor Raghu. There is one question from Gaurav in the chat box. I don't know if he's online. Professor Raghu, please go ahead with your question. Next, I'll take up Gaurav.
No, finish Gaurav and then.
Okay. Gaurav, are you there online? Yeah. Hi, Gaurav. Gaurav? Okay. So his question is, what is the criteria to select a 0 and a 1? Is it a unique threshold for all different places?
Okay, Gaurav, the threshold is not unique and the criteria are not unique in their quantitative way, but in the qualitative way, in the qualitative way, they're all the same. All the criteria are the same, but quantitatively, the criteria are different. For example, like if I look at one location, then like whether it's tied strongly to this side neighbor, it may not be tied same strength to this side neighbor as that side neighbor. So with that side neighbor, it may be tied very weakly, whereas with this side neighbor, it will be tied strongly. Hello? Hello, I'm hearing some noise.
Yeah, somebody has.
Shiva, can you mute Gaurav?
Yeah, I'm trying to.
Yeah, he's mute.
Yeah.
Okay,
Yeah, Professor Raghu.
So this was the question. This was the answer, that it depends. Like the broad thing is the same, but in numbers it's different. Yeah, Raghu, you had a question?
Yeah, so you mentioned Rishi's work with Subimal in the beginning. The goal there was to find clusters and see their relation to forcings from El Nino, PDO, NAO, and so on, and look for predictability.
Yeah.
And that here doesn't seem like you have looked for relations with external forcings for each of the clusters. So before going to climate change and how that will change the pattern, is there any work on predictability of these patterns? Because what is the ultimately you would want to be able to predict these things, I suppose.
Yeah. So that is to be done. Like we haven't done predictability yet, but like the first work with these joint patterns has shown that it's extremely interesting. And in fact, like we should try this with SST and many other things. In fact, we need not even be tied to the Indian landmass. Like you say, I can see whether the SST in another place. I can look for joint patterns between SST in some other place, or some other parameter in some other place, and and do the joint probability of that with us, and we could study forcing in exactly this way. So the difference between your work in or Subimal's work is that the difference between this and that is that there you were looking for yearly things, like how to represent years, and you were seeing whether like how each year is tied to the forcings around it. And that was a very, very nice study. It probably was done simultaneously when we were doing this. So like we have to take this forward into those ways. And I gave SST as one example. It could be a bunch of other things that we want to consider. So that would be it. And then like predictability should come next. I don't know like how predictable we can be on the local scale, obviously, because we are cohering things, but maybe we can predict like what's going to be tomorrow's pattern with something. And that's what our persistence matrices tell us. So like already we know with what probability it will go to which pattern tomorrow. So that much we already know.
Okay, thanks.
Thank you.
Dr. Rama, we have a question from Ranjit. Why not use deep learning instead of using MRF to find the pattern?
Okay. So like MRF is also a machine learning technique. What we've used is also a machine learning technique, because we've given it some randomized data and the machine has learned to bring out these patterns. So it's not too different. I mean, it definitely comes under the same class. So whether we should use deep learning with many intermediate layers, or hidden layers. Right now, this is like got one hidden layer, namely the Zs. The Zs are our hidden layer which take on values. So like we could add more layers to it, but yeah, it's an exercise which could be performed and maybe something interesting will come out.
Dr. Govindarajan. Yeah, Prof. Arpita has raised her hand.
Okay.
Since we do not have any more questions, and if time permits, I would like to. Okay, we do have one more question. Maybe we can ask.
My question is basic thing should be considered viral model. Okay, Vinod has asked a question. His question is, what basic thing should be
considered?
Can we
ask Vinod to unmute himself and ask the question?
Yeah. Vinod, are you there?
Hello, ma'am. Good evening.
Hi, Vinod.
Ma'am, if you try to model the spatial dependency between the two grid locations, and what should be the basic thing we should keep in mind while modeling like that?
Okay, so we have just looked at the last 8 years or 100 years of data. We just look at that and we say how correlated were these two locations. Like if it was raining here, was it also raining there? In other words, was the Z equal to 1 in both places? Were they highly correlated? If they were highly correlated, we give a higher value to that edge potential based on that data. So we fix it for all time based on the data.
Okay, thank you, ma'am. Thank you so much.
Yeah.
Any more questions? We are crossed 5 p.m.
Yeah. Maybe just one last, comment, Dr. Govindarajan, we seek from you.
I'll stop sharing, I guess.
Yeah.
Yeah.
Yeah, so we would like to hear your comments on, there are two different scales, and this question is not pertaining to this particular topic, but your research in general. that there are two different scales on which you are working, right? You are looking at finer scales, droplet scales, and also this, really large scale monsoon processes. So what are some of your insights? I mean, are they related? How do you integrate all of this together?
Yeah, brilliant question, Arpita. I keep wondering about this. Now the point here is the following. So you can have a cloud. Okay, the question is, will that cloud rain? Will it precipitate? Like, will the droplets grow fast enough? That's the basic question. And if the droplets will grow fast enough, it's going to give rain. So that's a micro scale question. And in the macro scale, we are seeing all this coherence in cloud, but we are seeing patchiness in rain. So that's clearly related to this microscopic question. So if we could solve the microscopic question, we could do better on the macroscopic one. We could have, a better Z thing, which has edge potentials to whether it's going to rain or not. And then you could have a cloudy system where locally I can say, will it rain or not?
Thank you.
Yeah.
Shiva, can we close now?
Yeah, we can close. No more questions in the sheet or in chat box. Meanwhile, I also want to request all participants to switch on their videos. We'll take a group photograph while Professor Arpita will, she closes the session.
Yeah, so heartfelt thanks to all the participants for joining in, listening to Dr. Govindarajan, and also asking really interesting questions. And thank you so much, Professor Govindarajan, for such a fascinating talk. And I would like to tell all of you that we will be having, a lot of distinguished speakers in this series, like of the likes of Professor Nandita Basu, Dr. Erika Coppola, and Dr. Freddy Otto, and so on. So please, watch out our Twitter space where Shiba would be publicizing these lectures, and join us for our year-long celebrations. Thank you.
Thank you for the opportunity.
Our pleasure.